We have seen so far the strain parameters, area calculation and few fault related terms and information on fault which are necessary for cross section balancing. Fold geometry extrapolation is also an important exercise. Sometimes it is done during the cross section balancing process. Let us study it. We are going to see two methods. The first one is the Busk method, also known as the curve deep domain method, and it produces parallel and concentric folds. Suppose this is the ground surface and we are thinking of a cross section, which means we are looking at a vertical section. The geologist at point A has found in the left hand side lithology P, and as he goes towards point B he finds lithology Q over here, and then as he crosses this point B following some scale and some geographic direction finds a lithology R. So, we are dealing with two litho contacts 1 and 2 and 3 lithologies P, Q and R. Suppose we are getting indication during field work that the lithology is folded. These are the folded Q layers, within B also some folding, and the folding pattern looks like parallel folds. That means they are constant thickness fold. These are the folds with constant orthogonal thickness. Now, here we will apply the Busk method or the curved deep domain method. It is an old practice in structural geology where parallel and concentric folds would be produced. What do? We transfer the information as per the scale and the geographic directions in the copy, and at this point and the lithological contact between P and Q we draw a normal that is extrapolated below the ground surface. We do the same thing at point B. At this point what happens? We find the lithological change from Q towards R, and this is the lithological contact. So, again we draw a normal and that is extrapolated below the ground surface. These two normals intersect at a point O. Point O is called the center of curvature. Next, to extrapolate the fold, we have to take a compass, put the needle over here and then take OA as radius and draw a circular arc, which I am going to show you actually on the paper, and again from taking O as the center. So, put the needle of the compass here and take OB as the radius, draw the other arc, and we say that this is the extrapolated fold geometry. And as you see, the extrados and the intrados of the fold are of concentric circles with center at O. O is known as the center of curvature. This is just a prediction and it need not be absolutely correct. In many cases it is possible that below the ground surface this is not the actual geometry. So, this is prediction and only one possibility. If we have found parallel concentric folds here or there in the terrain, then we can reasonably think this is a possibility, but with other geoscientific techniques we might need to cross check. We cannot take blindly this as the only possibility. Note the term deep domain, and what kind of deep domain we are calling? It is a curved deep domain. A deep domain means a domain of similar depth of layers. Here when we extrapolate the fold like this, we are thinking that all the layers are also folded in this way. Everywhere, say here, 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 here or here, we find a same pattern of the dip. The dip direction is the same, this is the dip direction, and here it is gentle dip, whereas here it is steep dip. So, some pattern is found so far as the dip of the different layers within this folded region, and that is why there is a deep domain and that deep domain is curved. A deep domain does not guarantee that the deep amount is everywhere the same. When the deep domain is curved, the deep amount can change. However, the dip direction remains the same. Now, what I have said here, let us execute on paper. Say this is the ground surface, some scale is there, some geographic direction is there. At this point, structural geologist has noted a lithological contact between lithology P and Q, and moving ahead he has found the lithological contact here between Q and R. So, there are 3 lithologies P, Q and R, and there are 2 litho contacts A and B. In my drawing, dip of PQ contact is less than that of QR contact. You can check later what if PQ contact is parallel to QR contact, and what if PQ contact dip is more than that of QR contact. On surface, parallel concentric folds have been seen here, here and there. I draw a normal to this litho contact and extrapolate it down the depth. I do the same over here. They intersect at point O. This point O is known as center of curvature. Curvature of what? Curvature of the folded layer. Next, take the compass, put the needle at point O, take the radius same as this much distance and draw a circular arc. Next, taking O as the center, take this distance as the radius and draw a circular arc. In this way, the folded layer has been extrapolated based on the Busk method, but this is not the only possibility. Other structural data are required to cross check whether this construction is correct or not. I said that a scale was used in the diagram to find out the distance between this point and that point, and this is the scale. 1 centimeter is equivalent to x meter. Once the drawing has been made, you can find out the depth of the center of curvature. From O, I will drop a vertical line on the supposedly horizontal surface and find out the distance. In my drawing here, it is 2.9 centimeter. Then I can apply this. If 1 centimeter is equivalent to x meter, then 2.9 centimeter is how much? The field case, the real case is called the prototype, and this few centimeters in my sketch is the drawing. So, from the drawing we can comment on the prototype at what depth the center of curvature of the folded layer lies. Now, I ask you to think, what if this is a situation, what if this is a situation? This method does not work all the time. It may be possible that when you try with these two situations, Busk method of 2 litho contacts and 3 lithologies and extrapolating the fold geometry may fail. You can check. Now, let us look at a situation when there are 4 lithologies P, Q, R and S. This is P, this is Q, this is lithology R and lithology S, and their contacts are marked at point A, point B and point C respectively on the topography. This is the ground surface. Consider this direction is y degree north and the scale adopted in the diagram is 1 centimeter is equivalent to x meter. Field geologist has brought this information and we are thinking that there might be regional folds present here. The field geologist got a hint because he is finding that the layers are showing parallel concentric folding here within P, within Q and then within R and S here also. Only with this information that there can be parallel concentric folds, the geologist can go for extrapolating the fold geometry, and again in this case only one possibility will be obtained and we cannot guarantee that this is the only possible case. The starting process will be nearly the same as we did earlier with 3 lithologies and 2 litho contacts. What is that? First draw perpendicular at point A with the litho contact, do the same at point B and the same thing on point C. Earlier we got a single center of curvature, here we are getting 2 centers of curvature. This point I can call O1 and this point as O2. What are O1 and O2? They are the centers of curvature of folded layers which I am going to draw. I am also extrapolating this line towards sky, but it is a faint line. This line also skyward as a faint line and the other line as well. So, at what depth O1 and O2 can be found? We can follow this scale. 1 centimeter is equivalent to x meter, and from O1 I can drop a normal on the ground surface, define the surface, and from here I can drop a line. This distance MO1 distance can be found out, say it is y centimeter, then as per scale if 1 centimeter is equivalent to x meter, y centimeter is equivalent to say capital Y meter. So, in this way the depth of O1 can be obtained. Similarly, the depth of O2 can also be obtained. From O2 I can drop a perpendicular line here and say this point is capital N, then NO2, suppose it is z centimeter, then if 1 centimeter is equivalent to x meter, then the small z centimeter is equivalent to capital Z meter. In this way the O2 depth can also be obtained, and one can also find out the O1 O2 distance vertically. What is that? From O1 I can draw a horizontal line and then find out this distance. Say this is T, then O2T is the distance between O1 and O2 measured vertically. Suppose O2T distance is equal to small a, then using the scale 1 centimeter is equivalent to x meter, I can find out this A centimeter is equivalent to capital A meter. In this way we can obtain the distance. If required, we can also do. Now, let us get back into extrapolating the fold geometry. The initial process is the same. Taking O1 as the center, I take this OA distance as the radius and draw a circular arc, but ensure that it ends over here. At this point it ends. Next, taking O1 as the center, I take this OB distance as the radius and I draw the circular arc, but not crossing this line. Between this line and that line I draw the circular arc, and a part of this lower layer that has gone outside this line is erased. I mean to say, this part of the line is cancelled. So, what has happened? Arc has been drawn here and over there with O1 as the center. Next phase, take O2 as the center of a circular arc. So, I am putting the needle of the compass at O2 and I am taking O2C as the radius and draw a circular arc, but stop over here. Okay. Note that this circular arc starts here and ends there. It does not exceed and does not go to this side of the line. It starts here and it ends here, or it starts here and it ends here. Next, maintaining O2 same as the center, I take O2B as the radius and draw a small circular arc. So, what I have done? Taking O as the center, I have drawn a circular arc now shown by a pen, and I have also drawn a circular arc shown by blue pen. So, these two segments have O2 as the center, whereas these two segments or earlier drawn have O1 as the center. The work is not yet over. This segment has intersected this line at this point. Now, what to do? Take O1 as the center and this point, let us call it point K. Take O1K as the radius. Now, unfortunately, in my compass it is not coming. So, I will do approximately. So, this was an arc with this center, this was an arc with that center. Taking O1K as a radius, I have to draw an arc. This arc is also having a center O1. So, these three ticks indicate three arcs having a common center O1, and in this way the fold geometry has been reconstructed. So, altogether how the fold is looking like? This is a single arc with O1 as a center. This one will be tricky. This arc is having center O1 and this tiny arc is having center O2. So, altogether it is not the arc of a single center or a single circle. This arc and that arc, they do not belong to same center. This arc belongs to O1, this arc belongs to O2. Okay. And next I will draw this here. This I drew by hand because my compass could not take care of such a big radius. Okay. And then from K to this arc KC is related to the center O2, whereas this arc is related to the center O1. So, how the folded lithology has been plotted? Lithology Q, which is folded, and lithology R, which is folded have been demonstrated. We have done with 4 lithologies and 3 lithocontacts. Suppose the number is increasing, there are n lithologies and n minus 1 contacts. In that case, similar approach will work. In this method, we have created basically 2 deep domains. We can call this as the deep domain 1. What is that? Bound by this line and that line lies the deep domain 1, and there is another deep domain, we can call it deep domain 2. This is bound by this line and that line. So, deep domain 1 and deep domain 2 are separated by the KB line. KB line separates deep domain 1 and deep domain 2. Sometimes the KB line is known as inflection line. You have seen the word inflection earlier in the context of fold geometry. For example, if there is a folded layer, inflection point is the point of minimum or 0 curvature. These points are inflection point. What are they? They are the points of minimum or 0 curvature in the fold geometry for a single layer. Since curvature is equal to 1 divided by radius of curvature, from here we can also say inflection point is the point of maximum radius of curvature. In this context, you have heard the word inflection, and not just point, but we are calling KB as the inflection line. Where is KB? This is KB. This is the inflection line IL. So, what I demonstrated here, I am now going to show you in terms of figures from the textbooks. Let us look at the textbook diagram for what I have done right now. First, one of the centers O was found out by drawing normals here, and then 2 arcs were drawn, and these arcs are restricted within these 2 lines, and this defines deep domain 1. Then a normal is drawn from this, and that intersects this line, that defines O dash, the other center from which these 2 arcs were drawn. Where this arc intersects this point was marked, and this arc intersects that point was marked. Next, taking O as center and this distance as a radius, this arc was drawn. So, this defines deep domain 1 here and the deep domain 2, and this is the contact between the 2 deep domains. This line is known as the inflection line. The geometry of the fold is important in hydrocarbon industry, and there is a very old anticlinal theory which says that simply where you can locate the hinge of the fold, go for drilling, you may get hydrocarbon. This theory is more than 100 years old. It was indeed applied to explore hydrocarbon. Initially some success was found, but then later failure happened, and at present anticlinal theory alone is not the guiding light to find out hydrocarbon. So, this anticlinal theory right now has only historical relevance. Suppose Along with Busk method and other techniques, we are able to extrapolate the fold geometry. Where should be the drilling site and how deep the drilling should go can be strategic decision.